Welcome everybody, either from the MaLGa group or the Ellis Genoa unit or remotely. So this is a seminar organized by the Machine Learning Center in Genova, and it's part of the activity of the Ellis unit in Genova. It's a pleasure today to have Alberto Bietti. Alberto graduated recently from Grenoble and is now in New York. He's actually been working on a range of different topics already, but I guess among the things that he's been doing, there is this there is a line of work where he tried to he has results trying to shed lights on how you can somewhat mix ideas from deep learning and kernel methods with all the challenges of deep learning and all the beautiful math of kernel method, and try to take advantage of the latter to explain the former. This being said, I hope you'll have fun. Alberto is a good speaker, so welcome, Alberto. It's a pleasure to have you here, even though remotely, and thanks for waking up early for this. We hope to be able to pay you back in person soon, as usual.
Great. Thanks, Lorenzo, for the introduction. Yes, of course, hopefully someday I'll be able to actually visit the center in Genova. Looking forward to that. Yes, so this is... the title is basically the title of my PhD thesis, actually, but there will be some refresher at the end that is a bit more recent. But yeah, so I've been working on trying to study convolutional models, so deep convolutional networks through the lens of kernels, which have kind of a nice mathematical formulation that allows us to understand some things better. This is, I started this kind of early during my PhD, and have been interested in the topic since. So hopefully I can give you an overview and a survey of the results here. Okay, so it all starts with the success of deep learning. So you probably all heard about these deep neural networks that have been very popular and successful in practice. So they're often state of the art in a lot of different tasks, and especially in ones where the data is this structured data like images or audio or text. And so the usual recipe to their success is to use these very large models that are typically consist of some compositional structure. So they have like a hierarchy of different functions that are composed with one another. So if X is maybe an image, here these W are matrices that are potentially structured, and these sigmas are nonlinear pointwise activations like this ReLU function. And the typical strategy is to make the models as big as you can with some specific architecture, then just feed them a lot of data, like this huge data set like ImageNet or even bigger, and then just put them on GPUs so that you can compute things very efficiently and use typically simple algorithms like gradient descent or stochastic gradient descent or variance. And this is usually worked very well empirically. And one specific kind of models that have been very successful, especially on images, is the convolutional architecture that dates back to work of Yann LeCun and other people at the time. And so the idea here is typically that you want to exploit information at different scales in an image. So perhaps the first few layers try to look at elements, something that is very localized in the image, like small edges or small corners. And this is, for instance, the kind of features that you can capture on the left through the first layers. And then later on, you try to aggregate these things and start looking at little neighborhoods, little patches, like little pieces of a wheel or pieces of a doorknob of a car. And at the end, you have these higher level features that hopefully capture more distinctively the objects. So, one interesting question is how can we try to understand these more specifically? And typically, there's some way that people think, there's some reasons for which convolutional networks are successful in images. So the way they work is they have these convolutions at each layer, which instead of computing a full matrix product with the whole input, they actually look at localized neighborhoods like these patches here. So instead of having a big matrix product, you have this very sparse kind of factorized model, which looks at the little neighborhoods. And you do this at different scales. So you have one on the patches of the original image, then one on patches of some subsampled image throughout the model. And at some of the layers, you do some downsampling, so pooling, which hopefully provides some invariance to like translations or shifts in the image. So, hopefully by encoding this information in the architecture, you're providing some inductive bias that allows you to learn more efficiently. So by putting this prior information about the structure of images in the architecture, hopefully you're hoping that learning will be easier and you can do it more efficiently with fewer samples. Okay, and lately, models have been growing. This is already very old. This is a VGG model, but basically the number of layers has kept increasing through the years. And now for the challenge of understanding how these models work. So there's been a lot of work in the past few years already, but the typical challenge is that because these models are very large, they're very over-parameterized. So classical theories that maybe count the number of parameters are basically doomed to fail because these numbers are so large that we can't really say much. They also are very expressive. So with those big numbers of parameters, you can essentially approximate any function often. So the question is like, why, if you can approximate any function, why would you choose one over another? And why is it that these models actually generalize well? The other thing is architectures seem to be essential, or at least in all the successful applications of deep learning typically use some like very advanced or well-designed architecture for the task. So how do we understand benefits of the architecture? That's another question. And finally, there seems to be some easiness from optimization. So we can just use simple methods like stochastic gradient descent, and yet we find decent models or good models that generalize well. So in this work, we try to view, kind of abstract away some of these complexity by studying models as functions from a functional space. So instead of it, we kind of ignore all the parameters in the model, and we just simply view these neural network models as elements of some functional space. And this gives rise to more traditional methods like non-parametric statistics, which allows you to kind of ignore the number of parameters and view the complexity as coming from some underlying measure of complexity, like a norm. And the question, of course, is what's an appropriate functional space? And that's not really understood in general for deep learning, but our approach will be to consider something that we actually know and at least in this group love. So the kernel methods, and as the title suggested. So this is kernels, they provide a nice way to linearize problems. So if you have some input domain here, X, so the set of images, the way kernels work is they kind of map all inputs to this representation phi of X, which is in a Euclidean Hilbert space structure. So it has this nice linear structure, and you map so each X to this potentially infinite dimensional Hilbert space H. And then you can learn functions that are essentially linear in this representation. So this f of X is actually an inner product between the function itself and the representation phi of X. So this can be, of course, nonlinear, especially when you have very large dimensional phi of X. And when you have this structure, often you can reframe the learning problems as learning from this positive definite kernel function, k of xx prime, which is just the inner product between the two representations. And because you're abstracting away the representation itself, you can even deal with the potentially infinite dimensional spaces. So often with these classical methods, you need to compute the kernel matrix, which can be very large, so n by n. But there are ways to alleviate this, and so this last point here is that this can be very costly to run kernel methods in general. But if the problem has some nice simplicity, you can typically do approximations. If you're familiar with random features or Nystrom methods, that's what I'm talking about. But overall, you have these clean convex models, so that they're tractable. At least we know that the algorithms will work when you use kernels like this. And they're typically convex problems. And we also understand the statistical and approximation properties for many kernels. So there's a nice toolbox that allows us to hopefully understand some things better. Okay, so what is the link between kernels and deep networks? So it turns out this has been studied for about a little over 10 years now. Actually, even earlier, I mean, some people have introduced this since the 90s, but let's see. So one way to see the link is just to simply construct kernels in a hierarchical fashion. So this was kind of motivated and studied originally in this paper by Cho and Sol. And it turns out that if you look at this representation phi of x, you can actually define it hierarchically through this composition with two different kernels, so phi2 and then phi1 of x. And if you do this, basically it consists of, if you look at the specific case of kernels on dot product kernels on the sphere, so which means that here phi of x, so the kernel itself is actually defined as some function of the inner product between x and x prime. And let's say we constrain x and x prime on the sphere. Then the outer one, you can call it, instead of basically taking an inner product between directly x and x prime, you might take an inner product between some features of x and x prime, which maybe themselves come from another kernel kappa 1. And so in the end here, what you get is by composing these feature maps, you actually get the composition of kernel functions. Okay, so it's a similar kind of kernel, but perhaps it has some different properties. Now, something a little more interesting is when you consider different architectures. So you can actually define kernels in a hierarchical way, in a similarly for more complex architectures like convolutional networks. So in this case, instead of defining, so we'll go through this construction later because it's kind of the main topic of the talk, but you can actually build these kernels on small patches of an image and potentially at different layers, and then eventually construct a full kernel on images by using these localized little kernels on patches. And this has actually worked well empirically. There's various works started by Julien Méral, but also more recently people have studied these even in the context of understanding these neural tangent kernels that I'll talk about next. But because it's costly, then there's often some tricks that you can do to approximate it based on the Nystrom method, for instance, and this leads to quite good performance that almost matches, let's say, the deep neural networks from 10 years ago. So it's not the best ones, but it's like still quite interesting, and it's completely unsupervised. And they also seem to work quite well when you have limited small data sets. Okay, so the second point of view for kernels and deep learning is this infinite width view of deep networks. So in this case, let's say, okay, to make things simple, we can focus on this two-layer network where sigma is a ReLU. So you have an input x, you take m different neurons. So m here is kind of the width of the network. And for each one, you have an input weight wi, then you apply the ReLU, and then you apply an output weight vi. And then, so if you're familiar with random features, and if you fix these first layer weights wi, okay, so in this first random feature view, we fix the first layer weights to just some random, maybe Gaussian weights. And maybe we learn the second ones. So this actually corresponds to learning with a random feature kernel that is an approximation of this expectation kernel. And this actually dates back to Radford Neal here, who studied this when looking at Gaussian processes for neural networks. But it's also been made very popular in kernel methods by this Rahimian-Recht random features methods, and more recently in the context of deep learning as well. So this is the random features kernel, and then it turns out that there's this other regime which people have found more recently that's called the neural tangent kernel regime, and this actually comes from when you optimize both layers. So perhaps you have both the VI as the second layer and the WI as the first layer that are trained using gradient descent with some initialization that is let's say Gaussian 0, 1. And in this case, it turns out that there's this nice paper that explains the behavior, which is when you have, with this particular scaling, if you have a very large width or like even infinite width, then it turns out that this linearized model, where you look at, instead of looking at the function at theta, you look at the linearization around the initialization theta 0. So this is basically a linear model because this first term doesn't really depend on the weights, and the second one is basically linear in the parameters theta. So this approximation even when you're very close to initialization, you can still approximate any function, including fitting your training data. While you do training, it turns out that you can stay close enough to this initialization so that this remains relevant, at least in this particular regime. And in this case, so if you view the deep learning training using gradient descent as this regime. Basically, you can view things as learning with a kernel. It's just a different kernel than where we saw before, where actually you optimize both layers. So in this case, the kernel that it doing gradient descent and going all the way to fitting your training data will be related to doing kernel ridge regression with let's say with a zero regularization. And the kernel you get here is this, you look at the gradient at initialization with respect to parameters at x and then at x prime. So this will actually, in this two-layer case, this will have two terms, one which is the same as the random features when you take gradients with respect to the output weights. But there's another term that takes gradient with respect to input weights, which will yield some other kernel that actually depends on the derivative of the ReLU. So like a step activation in this case. Okay, and one point to note is that both random features and the NTK extend quite nicely to deep architectures and actually general architectures like convolutional networks. So before I move on, if there's any questions so far, I can take a little break. Okay.
So actually I have one very quick.
Yes.
So when you say that they extend to deep architectures, you mean that you can, you can build like hierarchies of, let's say, random features.
Yeah. So basically, what I mean is that these specific things, if you take a normal neural net with a general architecture, at least convolutional or feed forward, and you take all the weights going to infinity with some specific way to take the limit, then you can show similar results on this kernel behavior of training. So with particular scalings on all the initializations, you can show that you essentially have this neural tangent, this like kernel regime, this lazy training regime, except the kernel will be something different, which is actually a compositional kernel. So it's a more advanced, complex kernel. That depends on the architecture, but not on the training.
Okay, thanks.
And so just since you took a break, but maybe I didn't hear you mention it, but this also depends on some of the initialization, right? I mean, you might end up somewhere else, even with this architecture. So the linearization might be bad, and you might end up somewhere else, which might be a more interesting minimum, right?
Exactly.
I never remember it has to be
let's talk about actually, yes,
small.
it's a good opportunity to talk about limitations. So this, this basically is saying that if you're in this regime, so this regime, it's true at least if you have infinite width. So if you go all the way to the infinity with the specific like 1/√m scaling, then it turns out that you're allowed to have this like very lazy behavior where weights stay very close to initialization. But in practice, when you have finite width, something else can happen. You can move a little bit more, and then the linearization breaks, and you have something that actually adapts to the data maybe. So in fact, there's a whole other line of research that's studying this, some more rich dynamics of training, like this mean field regime, where you actually have a whole distribution of weights that move in some way or another and can adapt to the data. Perhaps it finds some structure it does some like feature selection where you actually end up with identifying specific neurons' directions. So this is one big criticism of the kernel regime in the context of deep networks, that it doesn't provide any adaptivity to the data structure. And we'll get back to this maybe at the end, but it's important to keep in mind that this is one big issue. But this is something that you can already see with basically two layers. So like a shallow network, two-layer, fully connected. Then you have the separation, but it doesn't really, at least when you consider these convolutional networks, it's not that clear that that point of view captures the importance of convolution. So here, the point is that hopefully through kernels, you can already try to understand benefits of the architecture or of depth in different ways. Okay, so I'll move on to the first part here, which will be just about stability of convolutional kernels. So, we'll try to construct these convolutional kernels on images and try to analyze some properties like invariance and stability. That's the first part. So, okay, so as I mentioned, there's some kind of expected property. People expect to have these properties on convolutional models. So one is that it tries to capture information at different scales in a compositional way. So maybe you have some like compositions of or hierarchies of functions. And then you're able to model local stationarity, which means that kind of locally you have some function that depends on like a local neighborhood of the image. And then it's kind of the same behavior is applied all over the image. And then there's this translation invariance, which thanks to pooling, so pooling creates some averaging that gives you some shift invariance. And then hopefully at the end, your model, your outputs will be invariant when you like shift your whole image. So if this is a digit and you move it a little bit to the right or to the left, then the output is supposed to stay the same. But the goal here is, can we go beyond the simple shift invariance, and can we be a little more formal about the study of these properties? And there's one nice framework that this work will be based on, which is it has been studied in the context of a fixed representation based on wavelets. And this is the scattering transform, which I cite here by Stéphane Malin and Joan Brunat. And so here, basically, the goal is, when you have an image, let's say X of U, so it's a signal, okay, at each U is like the location where you are in the signal. Then instead of just looking at translation where you move each pixel by a constant vector, by the same vector at each location, you might want to look at different translations at each point of the image. So at each location U, you move things by some tau of U, which depends on the location itself. So you model deformations, which are a much richer group of transformations than just the translations. And somehow maybe you can hope that it captures certain regularities in natural data, like these digits here. So, you could think that, the deformation to go from one 4 to another maybe is not that big, like you have to move some mass somewhere. But to go from a 4 to a 5, this would be like you have to change things completely. So this would be like a much larger kind of deformation. Or let's say maybe from a 5 to a 7, at least you have like just a single piece. But so you could say that if you have a small, in some sense, deformation, then you want your models to be robust or stable to them. And this is what's been studied in this framework of deformation stability. So to be a little more formal, you can say that a representation phi is stable if, when you look at this deformed image, so L tau is the deformation operator, minus the representation of the original image, you're controlled by two terms. One which depends, okay, the second one here depends on like the largest possible translation. So it controls translation invariance. So you're hoping that maybe this constant C2 here, this constant C2 is close to 0, or very small. And then this first term here, so if you're a translation, this is 0, so it's fine. But if you deviate slightly from a translation, maybe you do like, if you do some like warping of the image, or like a zoom in or out by a factor 1 plus epsilon, then this will just be epsilon. So you're guaranteed, if you have such a relation, that you're guaranteed to stay close, even if you like do these small deformations. Okay, and then how do we, how do we do this with kernels? So as I said, the kernels allow us just to view these networks in a linearized way. So you have models that are actually linear in this representation, which depends on the kernel that you choose. And the goal here will be to study the geometry of this representation. And so if the phi mapping gives you something that is, translation invariant and Lipschitz, stable to deformation, then you will actually, the predictions of your models will also have this property controlled by the norm. So the norm somehow will capture complexity of the model. And then this phi here, the invariance part will actually be captured by the kernel itself, which is independent from the data. And it depends on the architecture. And okay, so this is useful both for the kernels that you can build manually in practice, but also for these models of deep networks. All right, so now I will quickly try to show how you construct these kernels a little bit more formally. So we start with a signal x0 here, which is defined on a domain omega. And then at each position u, so u maybe is like 2D, like a 2D point for images. So it's just a location inside the image. And x0 of u is the value of the pixel. So maybe it's like a RGB vector that tells you the color at that location. And for the study of stability, at least, we'll focus on continuous signals. So omega is just RD, just to, so that we can look at these deformation in a more intuitive way. And then we'll basically construct each layer using these 3 different operators. So the first one will be, so starting from x0, each time we'll construct these new feature maps, which will also be constructed on the domain, except that the values, instead of being just pixels in R3, they will be values like elements of some Hilbert space. So the first operation is usually you extract a patch locally. So this depends on the location. The second operation will be to take this patch and map it to some new Hilbert space through a kernel. And finally, we'll do some local averaging, so some pooling to gain some invariance. So the goal was so I will show you these operators a bit more formally, but the goal will be to essentially, at least in the study of stability, we'll control the norms of these operators, so we can control how these deformations or translations propagate throughout the layers. So the picture looks a bit like this, and let's start with the patches. So the patch extraction, basically for each location U, you grab a little box, so a little vector that looks at all the values of the previous image at centered at U, but also with all the V's around a little box. So here SK is this shape of the patch, maybe like a little square. And it turns out, so by looking at it, and if you define the norms appropriately, then you have that the PK is like a linear operator on this L2 space, and it preserves the norm. Okay, so that's the patch extraction. Just you kind of like vectorize things locally, and you repeat some of the points into these patches. And once we have the patches, then we map them through a nonlinear kernel mapping, which here is denoted phi k. So we take all the patches. So this is just a pointwise, this mk is a pointwise operator that grabs the patches and maps them to a Hilbert space. And you can see it depicted here with this new point. Okay, so what we will need is actually this phi. So for stability, this phi can be quite general, but we will assume that it's non-expansive, meaning that it preserves, so the norm is not greater than the norm of the original patch. So I have 0 patches here. And also like non-expansive in the sense that it's 1 Lipschitz. So you have, when you look at 2 different patches, then the distance of the representations is not larger than the distance between the original patches. And if you have this for phi for any given patch, then you also have this for the final operator, which applies on the entire feature map. Okay, and to see where this comes from, when you actually build the kernels, so you can typically what the kernels that are used in the context of deep learning is these dot product kernels. So one simple way is because when you have dot products, so these 2 Z's are themselves elements of a Hilbert space, so you can easily. So if Z themselves are based on some kernel mappings from the previous layer, then you can actually compute this using the kernel trick. So you can actually do your kernel computations hierarchically. But they also come up naturally when you study deep networks. So as I showed with the random feature models and neural tangents, it turns out that the kernels that you obtain are typically of this form, at least with the ReLU activation. Okay, so here each kernel on the patch takes these 2 patches, takes the inner product and normalizes it and multiplies by the norm outside. And we call phi k here the kernel mapping. And kappa here is typically of this form, so some kind of polynomial, or I guess analytic function, with the bj's are all positive, and they sum to 1. So when you take u equals 1, then the sum of bj's equals 1. Just a normalization that we can do. And so it turns out that if you have this structure, and if you additionally assume that the derivative at 1 is less than 1, then you have the non-expansive property that you need. So everything's great. And for some examples here, so what you often use in experiments is the Gaussian, so like a Gaussian kernel, which when you limit things to the sphere, it actually looks a bit like this. So you don't have a squared norm, you just have the inner product, -1, and you can put an alpha factor, some factor in front to control the bandwidth. Then you have this other example, and this last one is what comes out when you use ReLU features. So when you take this expectation that I showed before with W, there's like a Gaussian or just a uniform variable on the sphere, which is the random weights. Then you take this expectation and you get a function that I didn't write, but that is expressed, can be expressed in terms of the arc cosine of this angle, this like cosine of the angle here. And depending on the activation, you might get even different kernels. Okay, so this was the nonlinear mapping operator. And so the final operator is the pooling operator, which is essentially we're just averaging things in a linear way using maybe a Gaussian convolution. So here H sigma is like a Gaussian filter, maybe. And we do some local averaging at some scale sigma k. So if you normalize things appropriately, this is like an operator that preserves the norm, or is like non-expansive as well. And in practice, what you do is when you're actually in a discrete setting, so after you do this pooling, you typically like gain some, you like reduce some of the high frequencies, so you can do some downsampling. And we can also show some simple properties of how you preserve information as long as you don't subsample too much. But basically, this is to say that you can consider at each layer to like do the pooling and then kind of downsample so that you reduce the resolution. Okay, so recap these three operators: PK, patch extraction, and MK, kernel mapping, and AK is pooling operations. And when you define this, you can then construct this kind of like multiple layers, one after the other. And we will make one typical assumption, at least for stability, on the X0, which is the original signal, which is that it doesn't have too many high frequencies in the sense that it's itself, typically you have a discrete signal in practice. So the way to model the fact that it's discrete, maybe you can just say that X0 is itself some pooling of some natural signal X. So maybe A0 is like a camera, a sensor that you like take the measurement and actually locally averages information. You can view this as anti-aliasing. And the representation that we construct then has like, it just stacks a bunch of layers, so n layers here with all the three operators at each layer. And what would correspond to a practical convolutional network is to use SK, which is the patch shape, to be like kind of a similar size at each layer after downsampling, which correspond in this case to like sizes that grow exponentially. Because if you don't do downsampling, then it corresponds to just having things grow exponentially. Both the size of the patches and the size of the pooling operators sigma k. And once you have this representation, the kernel is basically given by the inner product here. And it turns out that if you use those dot product relations layer by layer, you can actually write down the full kernel. You can even evaluate it and compute it on real data. All right, so this was the construction of the kernel. And here are just some quick results on how you actually can show stability. So it turns out that you
Alberto,
can have...
Can I ask you a question real quick before? So just not to get lost in the notation. So this phi is the global one. Then the phi k are the one that go from one layer to the other. So that the inputs and the outputs are Hilbert spaces. Whereas xk is basically this phi up to a certain point. It always starts from the domain and you view it as going up to a certain point.
Yes.
So xk
also,
minus 1.
Right, and xk is also like a whole feature map. So for each point u, you have an element of hk.
Okay.
So, yes.
Up to floor k.
Yes, up to n, let's say.
Okay,
yes.
okay.
And so the small phi, they're applied on like locally, so only on one small patch.
And the fact that the patch's size grows exponentially is an assumption encoded somewhere, or
so here,
I guess we'll see it in the next slide.
Yeah, so for here it's not assumed, but it's a good way to like achieve stability. I will mention.
Yeah.
So one thing is, first, if you want to do downsampling, so if you're in a discrete setting, then you cannot have this downsampling to be too large. So we will assume at least that the size of sigma k actually has to be controlled by maybe the size of the patch. So sigma k cannot be too large compared to the diameter of this sk. And then some other thing will show up in the next slide, which is that the patches themselves cannot be too big if you want to have stability. So okay, let me go through this stability result. So as I said, we want to look at the difference in the final representations on the deformed image L tau x and the original image x. And here we assume that instead of x, this representation actually takes the anti-alias signal, so A0x. So for some deformation that is not too large, but this is still can still be quite large. It's a technical assumption, I guess. And if you assume that maybe the last size of pooling is sigma n, then actually, so the second term only depends on the last layer of pooling. So you have translation invariance kind of up to some scale that is governed by this last layer, sigma n. And if you fix this, maybe like a sigma n, you fix the final translation invariance that you would want, then there remains, both the number of layers that you have here. So for the stability part, you have this number of layers and then some constant that you can show that actually controls stability at each layer. So as you propagate things through the layers. And the C beta here, so beta is something that's around the patch size. So this was like the size of this shape of the patches at each layer. Okay, so actually in this case, beta is just the patch size in a discrete setting. So if you were, it's kind of like the size of the patch relative to the resolution of the previous layer, which means basically okay, so it's like the size of sk divided by sigma k minus 1. So after some pooling, we assume that the resolution is the scale sigma k. And so you want the patches to not be too large relative to that resolution. And so this constant actually grows with the patch size in a cubic way, whereas the number of layers, this is basically logarithmic. You can show that it's, if you want to reach, like to have something that is small on both terms, then you can typically take the number of layers to be logarithmic in the sigma n divided by sigma 0. So the number of layers grows very slowly with the invariance that you want. Whereas the patch size here is what most affects stability. So also the n here also depends on beta, but in a very minor way. So what's important is really to control this C beta term, which is small when you have small patches. So, okay, so you have two things to control. One is like this downsampling factor. And here we just said we cannot downsample too much. Otherwise, if you downsample too much, you lose information. So we say, okay, we limit the amount of downsampling that you can do at each layer. And this tells you that you need many layers. If your patches are small, you're going to need many layers. And if your patches are large, maybe you only need one layer. Okay, but if you use patches that are too large, then this will actually be much worse. Okay, so beta maybe will be the size of the image, or beta will be equal to sigma n. If you only use one layer, maybe beta has to be of the order of sigma n. Whereas if you use many layers, it's actually of the orders of log of sigma n. So you get this logarithmic, this exponential improvement in stability by using small patches and many layers. So, this shows kind of a benefit of depth in terms of the stability to deformation property. Okay, I hope this was clear.
Alberto,
yes,
I do. So, looking at these results here, I cannot see. So, are there any assumptions on how you build let's say the size of the patches and the pooling throughout the network? Because I mean, these results, if I'm not wrong, tells you that, I mean, the quantity on the right side depends on quantities like sigma n and Sn, I guess. So the last size of pooling and the last size.
So here I'm implicitly assuming that, okay, let's say that the size of patches grows with a fixed exponential factor. And the size
so this is something that I have to assume.
Yes. So I mean, the results can be written generally for any kind of layer, whatever you have at each layer, you can write some stability bound. Here, I'm just saying that one natural way to see the benefits is to use these like exponentially growing sizes. And then you can view n as the resulting number of layers, and then beta as the ratio of the patch size divided by the sigma k minus 1. So the size of sk divided by the resolution sigma k minus 1 of pooling. So that's basically, if you're using something in a discrete setting and you use 3 by 3 patches, then beta is around 3. These are the order of this patch. So the patch, like at each resolution, that's the patch size. And so this, if you use this like constant growth size of the patches and pooling, then basically things will depend on this beta, which is the patch size in a discrete setting. And it tells you that overall the bound will grow, depending on this patch size, and the number of layers is much, is relatively small. If you use a very small beta and you have many layers, you're still having a number of layers that is only logarithmic in the translation invariance. Whereas if you use a very large patch size, so then you need a few layers to achieve the same level of translation invariance, because you don't have to downsample, or you can downsample a lot. Basically, I'm saying that if you have like these huge patches, then you can downsample by the size of the patch, which is huge. So you need very few layers to achieve sigma n, but the problem is the stability bound will be much worse because of this beta will be very large. Okay,
yeah,
so,
thanks.
Cool. And so we have, okay, the illustration come later. So you can also do the same for this convolutional NTK. It's a bit more painful and you get some like slightly, instead of having the norm, the deformation bound, you have the square root of deformation. So it's a bit worse, at least for small sizes of deformations. And just for some quick simulations, if you take n-ness digits, so I don't really see the time, okay. Oh, wow, 39:45. Okay, so if you take these digits, you can look at small deformations of the digits and they increase kind of linearly with the size of the deformation. And all I'm showing here is that for the NTK, you can see that it's slightly faster growth at the beginning. So here I'm actually computing the exact kernel and looking at small deformations and see how the distances change with respect to the original image. So just a small illustration of these stability bounds.
Alberto, I lost it. So what is the convolutional NTK?
Convolutional NTK is with ReLUs, so same architecture, but okay, so if you look at random features with the ReLU, with the architecture that I described before, you get the same constructum that I said with the arccosine kernels on each patch. Okay. Now, if you look at
so you have to you have to start perfect. So you have to start patches and do averaging on top of that.
Yes, yes. So the same construction that I did is just you do it on the network. If you look at the corresponding random feature kernel, you get the same as what I described before. But for the NTK, you actually have a bunch of terms because you have the gradient with respect to each layer weights. So it's a bit more complicated kernel, but you can still get a bound. And actually, this square root comes really from the fact that you're using, when you do NTK, you have the derivative of the ReLU. So you have this like different arccosine kernel for the step activation. And this gives you a little bit less stability.
Okay.
Okay, just some quick empirical results. So you can actually compute these kernels exactly on CFAR, which is 50,000 images. And so you can compute these huge matrices, and that takes quite a while. So I have some, if you do it on like many different cores, so if you run it on like 1,000 cores, then it can take maybe a day or less, but it's still like a lot of computation. But once you have the full matrix, you can just do like kernel ridge regression and invert the matrix. That's actually pretty fast. So if you do it with just 2 convolutional layers and patch like subsampling sizes 2 and 5, then the NTK, it's a bit less stable, but you can see that it's a bit better at approximating maybe the task. So you get slightly better accuracy. And here, if you just use a Gaussian kernel, so I'm just showing that basically the NTK here is not a big picture, because if you use a Gaussian kernel, you actually get better. And if you use 3 layers, you get 88.2, which is actually maybe state of the art for kernel methods on this task. At least according, so this last paper here, okay, I didn't mention what it is this Shankar paper. So it's Ben Recht's team, the student. And they also get this 88.2% with, I think a more complicated kernel that has 10 layers and more different poolings. So here, maybe the benefit here is that we use Gaussian pooling, so it's kind of slightly larger windows, and you can achieve the same with like simpler architectures. Okay, so
so here there's nothing learned.
No, just you compute the kernel, yes, with a fixed, yeah. And this is the kernel that I use on the patches, exponential or ReLU, yes.
Yeah.
And you can also do data augmentation. If you like consider both the image itself and the flip, then you get a little extra performance. Okay, and I'll show a bit more results at the end if I have the time, but okay. Okay, so now we talked about these stability properties. So when we have this kernel, what are nice properties that all the functions in the RKHS possess? So they have stability and they have invariance. But the question is really, what are all the functions in the RKHS? So like, what kind of functions can you approximate with these kernels? And maybe all the translation, all these like stability to deformation and invariance, maybe that's not enough to guarantee, like you cannot approximate all of them. You cannot actually hope to reach all of them. And it turns out that that class of functions is a little bit too general. So if you have discrete signals, turns out that any Lipschitz function is also stable to deformations, just with some worse constants. But basically, Lipschitzness is enough to have these kinds of properties, which means that, so Lipschitz functions are very large space. They're very hard to approximate. So if you only assume that about your problem, it's typically not enough to get some easy learning, okay? So we need to get something more. And this is what hopefully I'll talk about in this section. Okay, so the goal of approximation is just to understand what functions are in the RKHS and what is their norm. Then hopefully we can try to get a sense of what convolution gives you that's better than fully connected architectures, and try to study the role of depth, okay? And we'll also see kind of coming throughout why the kernels might have problems, but I'll talk about this at the end a little more. Prelude, so one simpler result that I had, I guess in this first paper is that you can show that the kernels that I constructed before contain like functions that look like a CNN. So if you construct a function like hierarchically with different weights and different layers, you can actually show that it's included in the RKHS. The problem is that you need activations that are very smooth. So in fact, sigma here, it has to be some kind of polynomial or like a analytic function as well. And its norm, like the norm of the overall function will depend on this, this function ck sigma, which depends on how smooth the activation is. And there's the final norm, we can just show that it's, so this CNN with the same architecture as the actual construction will be in the RKHS, but the norm can potentially explode with the number of layers because it's like this stacking of different complexities. But at least in the, if you look at something linear, so linear activations, then, you know, it's kind of artificial, but it shows the scaling with this product of spectral norms, which is actually a quantity that's been studied in other areas of deep learning for controlling like Rademacher complexity of neural networks. So it can be maybe useful to control generalization. Okay, but the question that we'll ask later is, can we get a more precise characterization of the kernel Hilbert space using maybe tools from kernel methods that we know and love, that you know and love, that I'm learning to learn and love. Okay, so the fully connected case, at least the nice thing is that we have a nice structure that allows us to precisely characterize the RKHS. So similar to when you study translation invariant kernels, that you can diagonalize things in the Fourier basis and study exactly what the RKHS looks like. So for dot product kernels, you have rotation invariance. So if you rotate x and y by the same unitary matrix, then this is invariant to that transformation. And these kernels, as I said, they come from, you know, both NTKs and random features kernels when you have just a fully connected architecture. Okay, so in this case, you can actually give a precise characterization of the RKHS in terms of this basis of spherical harmonics, which is quite similar to the Fourier basis, except it's on the sphere. So it turns out that you can write this Mercer decomposition of the kernel. So you can, this kappa, you can actually write it in this eigenbasis YKJ, which is here K plays a role of a frequency. So K, you know, if you look at 2 dimensions, then this is exactly so the sphere is the circle, and this will exactly be the Fourier series on the circle, okay? But if you go to higher dimensions, you have like these other harmonics that come up, that you have a few more of them per each for each frequency. And you can study similar properties. And okay, so when you have this diagonalized way to describe the kernel, you can write the entire RKHS as containing functions in L2 that are written with this in this decomposition on the Fourier basis. And you have a way to control the norm that depends on the eigenvalues here, mu k of the integral of the kernel, basically. Okay, so in the fully connected case, this seems like a clear picture. And what can we say about it? So at least for the ReLU, for the case of ReLU networks, we can try to say, oh, is there any benefits to the NTK versus the actual random features kernel? That's an interesting question. Can we also study maybe deeper networks? So that's another question. And the framework that we're going to use is this, basically Francis Bach has this, this paper where he studies essentially for ReLU networks for two-layer shallow ReLU networks, the decay of these eigenvalues. And in fact, if you look at the previous formula here, depending on how fast mu k decays, this is going to impose, the smoothness of this coefficient ak. So ak will have to decrease very quickly if mu k decreases very quickly in order for this norm to be bounded, which will tell you like how smooth the function have to be in order to be in the RKHS. Okay, so this decay is basically very closely related to regularity in a similar way to, let's say, the Fourier case. And typically for polynomial decays, which is what happens for ReLU networks, we have norms that are quite similar to a Sobolev norm. So basically the RKHS norm will be similar to looking at, so here this delta is the Laplace-Beltrami operator on the sphere. So it's a bit more like nonlinear, but it's you have some power here that depends on some order of smoothness. And so it will be very similar to Sobolev spaces, if you're familiar with that. And so basically the goal is to find this beta for the different kernels that we're studying. And this will give us various, both conditions for being in the RKHS and rates of approximation, maybe for Lipschitz functions. So one thing you can do is show that the NTK is slightly larger than the random features kernel. So in fact, this beta, okay, so this should be, so D, let's say D is the dimension of the input vectors for the fully connected case. And so for the random features, you need beta slightly larger, so you need a little bit more smoothness in your space. Whereas for the NTK, you only need this P over 2, which is dimension divided by 2. And in order to be a kernel, you need at least beta to be at least P minus 1 over 2. So we're close to the largest possible space, but not exactly. And then one other thing that you can do is study deep networks. So this is more tricky because you cannot actually compute the eigenvalues exactly. But what we actually show in this more recent paper is that you can actually study precisely the eigenvalues. So you can precisely find the decay for these eigenvalues by just looking at like an asymptotic expansion of the kernel function. So kappa here is, as I said, depends on some like arc cosine functions, typically for ReLU networks. And it turns out that, okay, if you can write it, this expansion around +1 and -1 in terms of some non-integer exponents. So nu here is like typically 3/2. For the arc cosine function, it's like 3/2 or 1/2, depending on which kernel you use. Then this nu will actually govern the final rate of decay, and so the size of the RKHS. And so one thing you can show is that if you have this random feature kernel and you actually look at the deep network version, then actually these two kernels have the same decay, so it's basically the same space. So essentially in the kernel setting, there are no real benefits of depth. Okay. And the same is true actually for the NTK, just the neural tangent kernel will be slightly larger, but adding depth will not help much in terms of approximation. So some consequences of this result is that, okay, if we want to understand benefits of depth in fully connected networks, something more than kernels needs to show up, because otherwise we will not see the gains. And potentially, even within a kernel architecture, we need to go beyond fully connected networks and try to study convolutions. So this is just some empirical results to show this. So these are like various, okay, here we have some target function, and I show kind of the expected approximation error, or like just the generalization error for different sample sizes. So here everything is the same, which shows that if you have a function, essentially at the end, the complexity will depend. If you can allow yourself infinite computation, it turns out that both kernels, NTK and random features here, adapt to the data in a similar way. They give similar rates. But if you limit your computation, okay, so if you have, so basically the regularization parameter will be have to be a little smaller for the random feature kernel because it has, the space is a bit smaller. So you need larger norms and hence smaller regularization parameters. So if you limit the smallest one, so basically the NTK can go a bit further. And here this lambda min is kind of like proxy for computational power, because it's, if you're doing optimization, it governs like the condition number, and so how hard optimization will be. And so if you use a larger kernel typically, and you're approximated a very complicated non-smooth function, then you might need a little bit more a little bit less computational power with the NTK. And on the right here, I'm just showing that actually if you use random features at multiple layers, it doesn't help. So it's actually worse than if you just do the standard random features. And this is because, in fact, when you have a given kernel decay, given decay of the integral operator, then there's results that show that the number of random features that you get just with the standard two-layer network is actually optimal. So anything that, even if you add additional layers, you might actually need even more random features, which is suboptimal in this case. But this is just empirical, so potentially it can be interesting to study the approximation error with random features in a more precise way. Okay. Yeah, and then you can look, if you use these fully connected kernels, what happens on MNIST or fashion MNIST. Basically, the performance doesn't change much when you increase the number of layers. So there's one slight detail, which is from 2 to 3 layers, so actually when you only have a single layer, a shallow architecture with a kernel, you actually have some coefficients that are 0 in this Fourier expansion, which leads to some constraints in terms of parity. So for instance, you can only approximate either even or odd functions. Whereas when you go to 3 layers, that goes away. But there's other tricks to like fix the 2-layer kernel so that it actually becomes universal, which means that you don't have this constraint on the parity of the functions anymore. Okay, I think we might be almost running out of time, so maybe I'll go. Yeah. Do we still have time, or?
Yeah, we're more or less done with time.
Okay, so maybe I'll just briefly mention some more recent thing that is not yet online, but it should be on the archive soon, which is just motivating the problem of approximation when you have convolutional structure. Yeah. So here the point is like you have your inputs that are images, so these very large dimensional objects, and if you're trying to approximate any function defined on the signal, you're typically doomed because it's very high dimensional, and you will need some number of samples that is typically exponential in the dimension. So we need to assume something more about the functions. And one simple assumption that you might want to add is just that the functions are localized here. So instead of depending on the entire signal, maybe you depend only through like a patch of the image, which here I write this px with the same operator as before. So if the function only depends on the patch, then actually a fully connected kernel will not be able to really adapt to this structure. So it will still have to pay something exponential in the dimension, which is something like the size of the domain. Whereas if you use a very basic convolutional kernel like this one that I'm showing here, which is just a sum of like these small patch-based kernels, then this kernel, on each given patch, this is like a dot product kernel that only depends on the dimension of the patch. So instead of depending on this whole omega, you depend maybe on this patch shape S, which is a much smaller dimension if you use like 3 by 3 patches. So, one of these kernels will contain functions with a much smaller norm. And if you just take the sum, potentially you can find these functions even if you have multiple patches and somehow mix them. Okay, so these kinds of localized kernels, okay, just to put a plug here for your alumni, there's some papers that also use similar kind of structures for structure prediction. So it can give you some statistical benefits in these kinds of problems. And okay, so one thing that you can do is study this with pooling. So what does pooling bring to the picture? So in this case here, all I'm doing is adding this extra pooling, which is kind of averaging over your functions. And when you add this pooling, you can precisely describe the functions that are in the RKHS, it turns out. So in fact, they're typically written as the sums of functions. So for each position in the image, you will have a function inside the RKHS of the patch kernel, which is H here. Okay, so each G of U depends only on XU, which is the patch centered around U. So these are functions that depend on like a low dimensional object, so they don't have to be, they can be quite, because the patch is small, these can be actually quite non-smooth and you'll still be fine in terms of the norm. What pooling does, it enforces additional regularities on these functions. Okay, so this is a bit less readable, but essentially the actual norm that you get on this function f, it's like, okay, so first I'm writing the penalty in terms of g. So typically, if you have different g's that lead to the same f, then you will have to take the norm will be the minimum norm over all of such decompositions. But here, okay, this a operator, when you take a to the minus transpose, so just the inverse of the transpose of a, what this is doing is basically, if you think about it in the Fourier over the spatial domain, so just the location of these functions g of u, you're trying to encourage smoothness with respect to the spatial variable, okay? Because a, in the Fourier space, the frequencies of this a, so a is like a pooling filter like this, it's like very localized. So a minus 1 will be like the inverse of that, so it will be very large for high frequencies. And somehow this will encourage your functions gu, as I write here. So the pooling encourages smoothness of the functions gu of z for a fixed z, which is maybe represents a patch, but as a function of the location. So you want the different functions used inside the image to depend smoothly on the location of that specific function. And in contrast, at the same time, you'll have some control of each fixed function g of u as a function of the patch vector itself. And that smoothness will be controlled through the usual kernel dot product kernel. But you have some kind of mixing of these two regularization operators, which I write here using this tensor product notation. So you're somehow controlling both smoothness with respect to the spatial location and smoothness with respect to the input patches. Okay, so this is kind of a warm-up. And just one realization that comes up is that when you look at deeper, so first of all, so typically one-layer convolutional kernels don't do very well. So in this situation here, we're using like 3x3 patches of the first layer, which is good for alleviating the need of the dependent on dimension. But so this last layer here doesn't do very well, 74.2%. This is on only 10,000 data points, so it's a smaller sample, but you can compute the exact kernels. Whereas if you use 2 layers, then you get like 80%. So it's a big drop to just use 1 layer. And even if you use bigger patches at the first layer, it doesn't exceed typically 75 or something percent. But in contrast, if instead of using like a full 2-layer kernel, you use something with a simplified kernel here, like a polynomial kernel of degree order 2 or 3, then the drop is much smaller. Okay, so with polynomial of order 3, you actually get basically the same performance. Order 2, you get maybe 1% drop. So the fact that you're having something nonlinear is already very good. It captures whatever the kernel is trying to capture. In contrast, if you put a weaker kernel at the first layer, that already loses much more. So you lose like 3% here. So it seems like the first layer, it's important to have something very rich that can capture like complex functions on patches. But at the second layer, maybe you have these polynomial kernels that seem to be enough. And so what you can try to do is then for these simplified kernels, try to like characterize your RKHS precisely. And so this, you can actually do this. I won't go through too much into detail, but you can do this with tensor products of kernels. And in fact, what this does is when you use like the polynomial kernel of order 2, this will actually look at 2 different patches in the image, depending on like, and which ones you're allowed to look at actually will depend on your pooling and patch sizes at the second layer. But basically these kernel tensor products allow you to like capture interactions between 2 different areas of the image. So somehow you can view like, and the RKHS for this tensor product is actually much smaller than if you were using like a fully connected kernel on the combination of patches. So if you use like Sobolev spaces, typically the functions, the regularity that you're imposing on these joint functions is much stronger. So you have, so anyway, there are ways to see it in terms of this mixed smoothness. So typically you need, actually, in fact, the decay of the operators typically only scales with the dimension of the patch and depends only logarithmically on the number of patches that you're looking at. So there's some benefits in terms of statistics as well. But basically we're trying to like model this behavior on different patches of the image at the same time. And if you have a polynomial degree of order 3, then potentially you look at 3 different patches in the image and trying to model their joint dependence. Okay, so this has been studied in the actually recent papers also in the context of kernels, of convolutional networks, but also it's been very popular since the 90s. It was used as like these interaction models, additive splines. So the goal that what you can try to do is actually highlight the role. So it turns out practically, if you don't use pooling or small patches, it actually works very poorly. So if, for instance, if you don't use pooling at all, you would get something like 40% here instead of like 70%. So it seems like, so when I read this, in fact, this other paper tries to study precise decays for these kernels. But if you don't put pooling in the picture, it actually doesn't seem to be a practical method. So it seems crucial to understand the role of pooling in this approximation properties. And okay, so what you can do here is try to look at both the pooling and the patch sizes and see how they encourage additional regularities between these interaction terms. And so I have a slide to just briefly talk about it, but it's a little ugly. But okay, so when you use like a quadratic kernel at the second layer, basically you have the feature map that has these, like the outputs that are in this space. So instead of having only H, you have this tensor product, and then you have a certain number of them, which depends on like the size of the patches of the second layer. And the functions that you get actually capture these pairwise interactions between. So here, if you ignore this first sum, you have like functions that depend on the locations U and V, and they look at different patches with location U and V for all possible positions, pairs of positions in the image or the signal. And so why is there this PQ here is just within, if you look at the second patch, it actually encourages different kinds of interactions on each of these GPQs. So in particular, you have a constraint on each of these, which means the GPQ has to be localized. So you don't have to understand what it means, but just from the picture here, so it turns out that these 2 points are actually on a diagonal. So here, maybe the x-axis is U, the y-axis is V, and it just tells you that if you're pulling at the first layer is actually localized, so you don't have you only have support somewhere near the origin. Then basically your mass of the function GPQ, it can only be non-zero for when U and V are close to this diagonal. So here I'm just showing 2 points, which is the 2 different Diracs that you can put in here. But so this is a constraint that tells you, different GPQs will look at different parts of the interactions. And then within that, the final norm that you get is something like this, which is a little hard to parse. But essentially, you can see this, what's inside this diagonal term is actually looking at some kind of 2-dimensional smoothness. So you're encouraging your interactions here, GPQ, U, and V, to not depend too much on the positions U, V. Okay, so you're encouraging all of this to be like smooth as a function of U and V for fixed patches. And you can view this again in terms of like a Fourier penalty of the spatial dimension. And in contrast, the second layer, A2, which typically has a larger bandwidth because it's kind of a pooling layer, this one will actually look specifically at a given diagonal and impose a regularity that's a bit larger. Okay, so this one will actually look at just a single, so instead of having this 2D smoothness, you're encouraging something that's even more smooth, but only across one diagonal. And so one way to see this is that the GUV, it has to, so it's allowed to depend very weakly on like a global position of U and V, and it's allowed to depend a little more strongly on like the relative position between the two. So this is one way to interpret this norm. At least I think that's one interpretation. Okay, so you can have extensions. One point is that just beyond 2 layers, it's still unclear if kernels are very useful. So in fact, I can get on the CFAR data set, at least with just 2 layers, you can get basically the best performance. So yes, just to conclude quickly, okay, we've seen benefits of convolutions both in terms of stability and approximation at the end. We saw that for fully connected networks, the kernel picture is a bit limited. It basically is the same functional space regardless of depth, at least for ReLU networks. So, open questions. One is like, can we try to understand something where the kernels might provide benefits beyond 2 layers? That's would be interesting, but maybe it's not really the point of kernels. But at least we get some benefit of depth beyond 1 layer, which is already interesting. And second, of course, is trying to get a better handle of the statistics. You know, what are statistical properties of these models? And of course, there's a lot to be studied beyond the kernel regime. So, you know, one thing was feature selection, which is missing in the kernel picture. So potentially, if you learn the weights at the first layer, you can actually reduce the dependence on dimension even more by adapting to lower dimensional structures. And another thing is when you have deep models, you can hope that, you know, you can learn maybe some hierarchy of functions where, you know, for instance, the second layer might capture these interactions, but in a way that's a bit more learned rather than fixed by the pooling architecture. So these are all interesting questions for the future. Okay, thank you for your attention.
Thank you, Alberto. I guess there is me clapping.
Okay.
All right.
Okay.
I don't know if there is time for a few questions. We're a bit over time, but
yeah, sorry for okay.
Or is it happens? So I guess maybe I can ask a bit of, you know, like this was very interesting. There are a lot of connection and interesting points. I guess one general thing I'm thinking about is, I always wonder, I think this point, I think is really necessary to go and start to put this much more structure when you think about kernels and you start to really look at, you know, you have to think about patches, you have to think about pooling and this kind of stuff, because otherwise, I think one would only have a very limited understanding of what's going on with the architecture that really works in deep learning. I also wonder what is the natural way to think, what kind of properties should we look at? Because in some sense, if one looks at eigenvalues and stuff like that, these are very global properties. You end up thinking about it in terms of Fourier and so on. And so, yeah, I wonder what is the, because in some sense you could build spaces that are all Fourier, okay? But then they are somewhat described by different, you know, layering of structures. And then this might give you the opportunity of looking inside, searching inside of this space in different ways. For example, if you build the last kernel, there are hierarchicals, maybe the overall space is, you know, is the same if, for example, you stack up layers or you look different localization, but because you build them in a specific way, you can, you know, search inside them in different ways. So I wonder what is the best point of view, because in some sense, if I end up just thinking about, okay, what is the largest space, I lose a bit how I built it, and that they can all be the same, they can all have the same eigenvalue decay. But I wonder if this is the right point of view. And for example, how would, if you know, this last example, I think is very interesting because it's very structured kernels. But I wonder if you go in and look at its smoothness, probably will be just a poor Sobolev space where you lose a bit of interaction between all the variables because one connected a bit. And I wonder what is, from a functional point of view, what would be the, aside from say the stability point of view, what will be the natural way to characterize them? Maybe a new notion of approximation or stuff like that. I don't know. I wonder if you have thoughts about what would be the right functional point of view to study these spaces.
Yeah, so you're saying like maybe if there's a specific set of eigenfunctions that describe it, or?
Yeah, or maybe you know, I have to look at more like not one space, but you know, more to resolution point of view where I have really different spaces, and the notion of smoothness is not just global, like the eigenvalue decay of the given eigenfunction of the covariance operator, but more I think of the interaction of different covariance operator at different scales, and how I can somewhat describe a function that has, you know, for example, depends, you know, globally on a patch, but very locally among patches and stuff like that.
Yes,
This is not captured by just an eigenvalue analysis, I guess.
That's true. So that's why I think just viewing things here as like these decomposition, like additive models, at least it gives you like an idea of how, you know, it doesn't just gives you, okay, this is the full, you have a single operator. It just kind of tells you a bit more how this operator is structured, but it still seems like a single operator that is structured, that incorporates all the structure into like a fixed way that depends on the architecture. But I don't know, can kernels really describe things beyond like a single eigenfunction decomposition? I feel like
I don't know
you're
if
still
you think
stuck
of
with
you know, the whole point of your multiple kernel learning was basically about that.
Right.
You put
Okay.
different norms.
Okay. So
and
something
like
a little beyond the fixed kernel, maybe. Yes.
Yeah, it's because, but you have many kernels, right? Because your fixed kernel is made of a lot of kernels that you somewhat patch up together in a complicated way. So this sounds like a multiple kernel thing.
Yes, except that here everything's kind of combined in a fixed Euclidean way, right? So
yeah.
No, but
so maybe the last one.
Yeah, but I agree that it's interesting to like see how a little more structure can be extracted or learned potentially from these kind of constructions. Yes.
Okie doke. All right. I don't know if there is any question. Can be a bit long, but okay. So
yeah,
otherwise, thanks Alberto.
Okay.
There was a few questions along the way. Thanks a lot. It was a pleasure to have you. We hope to have you soon.
Many possible